Okay, good morning class. And then before I start my lesson, a student from other class has asked where to get the notes, okay, of my lessons. So I would like to remind for those who still do not know where to get my notes, you can go to UFuture. Okay, here is the interface. Can you see the UFuture interface?
Yes.
Okay, so you just go to the course content. I hope the interface from my view is same with yours. Okay, so you just go to course content and seek for my name. Okay, so once you enter my folder, okay, you can see here there is 3 folders. Okay, the first one is lesson plan, which if you I have also put in your WhatsApp group on the latest lesson plan that incorporated the dates of the test. Okay, so I have also uploaded in this folder, and the notes, and I also created a new folder this semester for any video that I have uploaded on YouTube regarding this the course. Okay, on the notes you can download the notes from this. Okay, for chapter 1 I do not put in the folder, so the one that is left outside are for chapter 1. Okay, for chapter 2 flexibility method, if you go in the folder, yeah, this is all the notes, okay, that you can download. Okay, now we are at flexibility method or the Truss examples, so you can download this for your use. Okay, and we are going every week we are going to have a new structure. Okay, application of flexibility method on this new structure. So for example, next week we are going to go for beam, okay, and then the frame, and then arch and composite. Okay, but the principle of flexibility method is the same, the procedure is the same. Okay, only we need to do some modification or treatment. Okay, so we are about 3 to 4 weeks on this application, so that you can get yourself familiar with this method. Okay, so I go back to the notes. Okay, you can also see other chapters. Okay, the notes, you can explore it. Okay, so you can give me feedback if you need more examples. Okay, so now I'm going back to my lesson. Okay, so again, these 2 classes will be on these 14 pages of examples on the trust analysis. I have briefed you on the example 1A, okay, and 1B, which is on the solving the indeterminate trust, dealing with 1 degree of indeterminacy, okay, which you need to remove 1 redundant force. Okay, so and today I'm going to share with you what if D is equal to 2, where you need to remove 2 redundant forces, okay, in the indeterminate system. Okay, so probably I need to again to open my introduction slides. Okay, on this let's have a look on the revision. Okay, hi class, can you see my slides on this procedure of flexibility method?
Yes, doctor.
Yes, sir.
Yes, doctor.
Okay, so right now we try to get familiarize ourselves, because this is a new method for you. Okay, but we are going to go through a few classes. Okay, we are going to practice again and again this procedure, okay, but apply on different types of this structure. Okay, so right now, once you have known get the problems, okay, of indeterminate truss, okay, what you need to do. So first of all, you are going to identify how many redundant, okay. So let me just make it. You need to know how many redundants that you need to remove, okay, so that the indeterminate system become determinate system. So you need to use these equations, okay, to get the value. Let's say now in our example today, we are going to get d equal to 2 degree. Okay, so what you need to do, you need to create one type of structure named primary structure and another structure named redundant structure. You will always need to construct only one primary structure. Okay, so I put it here, one only. Okay, but you need to remove n unknown redundant forces. This n will depend on your d. I would say that n is equal to d. So now in this case, you are going to remove two redundant forces. Okay, and then you remain all real loads. The real loads is still applied. For the redundant structure, you need to construct d numbers of or n numbers of redundant structure. So in this case, if your d is equal to 2, you need to construct two redundant structure. Remember, your primary structure and the redundant structure right now are all determinate. Okay, they are only imaginary. Okay, in this flexibility method to solve for your redundant forces. So okay, for this redundant structure, what you need to do for the first redundant structure, you need to okay, wait. So how about the geometry of the redundant structure? You can actually adopt, okay, whatever you have found from primary structure. You can copy and put it in this redundant structure. The geometry and the support. Maybe I will write here the geometry and the support. Okay, you can exactly the same with the primary structure, which these redundant forces has been removed. Okay, but now you need to do some treatment to your redundant structure where you remove all the real loads. Then you apply back redundant force 1 kilonewton. Okay, this redundant force, I would say 1 unit redundant force because it would depend on type of structure. It might be in the 1 kilonewton, it might be in 1 newton, it might be in 1 kilonewton meter. So it depends on what type of redundant force that we want to apply. Okay, so now this redundant force for redundant structure number 1, now you have two redundant structure, right? Okay, for the first one, you apply back the redundant force number 1 with this 1 unit force. Okay, for the second redundant structure, you apply back the redundant force number 2 with this 1 unit force. Okay, this unit force can be either externally or internally. If you still remember, externally I have introduced you that it will be referring to the support reaction. Okay, and internally we'll be talking about axial force, okay, in your truss, member truss. Okay, then you need to analyze both of these truss. Okay, so let's go to our example of today and have a look on how to apply these steps in a problem, a given problem. Okay, so I have put this in the PP in the PowerPoint form. Okay, but the detail is actually captured from this PDF file. Okay, you can download my notes. Okay, so now if you look at, I'm sharing you on how to solve example 3A. Can you see my example 3A class?
Yes, doctor.
Yes, doctor.
Okay, thank you. So now let's have a look on what is the statement of the given problem. Okay, so a pin jointed truss. okay, pin jointed. So actually to get this proper, you shall have a symbol of pin here. Okay, normally it be in a circle. Okay, so if you got my notes, you can help me to uh, uh, put these circles, okay, on this, okay, to indicate the knots, the joints, okay. And then it has been fixed at A and E. Okay, this is quite confusing. Okay, fixed support. Okay, but because normally about fixed support, we have a moment at this A and E, right? But owing this nature of the truss, that the truss, pin jointed truss do not take any moment. Therefore, at A and E, there will be no moments. Okay, they will be having only uh, this AX and AY. EX, EX, and EY. So there is no MA and ME in this case. Okay, and we have a roller at C, okay, which we have CY. Okay, so now it said take a reaction at C and member AD as redundant. Okay, remember, uh, don't expect this in your test, okay, or other problems, or real problems. Okay, this is normally will not be given to you. What are the redundants? Okay, you are the one who need to decide which one to be removed. Okay, so the tips is just make sure this structure is at a stable condition. Okay, so you can remove any of your support reactions or member forces, okay, externally or internally, as long as the determinate system is a stable system. Okay, and you can solve it with this equilibrium equations. Okay, so now it said that CY, please take CY as redundant. Okay, and take member AD, should be member force AD. Can you help me? Member force AD as redundant. So FAD is redundant. Okay, you can set FAD is redundant 1, CY is redundant 2, there is no problem. Okay, but both these forces are redundant. Of course, you need to identify how many from this equation. Okay, here you get the 2. Okay, so now find the member forces by using the flexibility method. Be careful. In your test, you need to answer the test according to the instruction. So now request you to use the flexibility method. So we are going to apply what we have learned in last lesson. Okay, and given L over AE is constant, because from the observation here, you will know that all the L is not constant, right? For example, DC, the length is 1 meter, but BC is not 1 meter, is greater than 1 meter. But now this problem has been fixed that such that L over AE is constant. Probably the A also different, okay, in between these members, and probably the E, but normally the E will be constant for a system, a very small system like this. Okay, so we need to know that this L over AE will not be put in your tabular form later. Okay, when we do it, because L over AE is constant. Okay, for all members. Okay, now since the fractional effect is neglected here, I put the tips here, okay, to just to tell you that the moment, okay, is not considered as support A and E, means that MA and ME, yeah, is not considered. Okay, so let's start with drawing the end node or primary structure. What we should do in the primary structure is we need to remove these. We will have only one primary structure, right? And then we are going to remove all the redundant forces. Okay, so yes, now this is the real structure. Okay, this is the real structure. Now we want to modify it to become the primary determinate primary structure. Let me have a look first. FAD and CY. FAD and CY are the redundants. Okay, so when you want to create your end node or primary system, we take out, we remain the load, and we take out all the redundant forces. So now CY, I take out. Okay, it's supposed to have CY, I take out. And then FAD, I take out, or it becomes 0. It's 0, or if you don't want to confuse yourself, you just take it out. Okay, so here, you get this primary structure. Okay, where your CY is removed, no more, and your AD, okay, has been removed. Okay, then you need to solve this primary structure to get your end node. End node is the exoforce. I named this primary structure end node as well. Okay, but the end node that we want to put in the compatibility equation is the exoforce for this primary structure. Okay, so let's have a look back on this system. Okay, how about primary redundant structure number 1? Okay, just now we have removed this CY and remove the AD, becomes 0. Okay, right? So now we want to create N1, let's say, where the CY is my R1. Okay, so now I will remain all the geometry and the support from the primary structure, not from the real structure, from the primary structure, which is already determinate system. And I need to remove all the real loads. Here now, I remove the real loads. Now I'm creating for N1. And I need to apply back the 1 unit force for my redundant 1, which is CY. So CY, I will apply 1 unit force. Okay, so this is how you create your N1. This unit force, either upward or downward, is just an assumption. You can't decide, make any assumption. Okay, but the direction must be same with CY. You cannot put it, I mean CX, okay, 1 unit force. No, it is to put it at the R1 position and direction. So now I'm going to show you on how to create the N2. Okay, I'm going to do this. Okay, again, just now in the determinate primary system, we don't have this and we don't have this AD. Okay, so now I'm creating this N2, where my R2 is FAD. I need to apply force at this for this R2. And again, I take my geometry supports from primary system. I remove all the real loads. Okay, so initially AD is not exist here, but now I need to apply back FAD equal to 1 unit force or 1 kilonewton. Okay, so now you can put it either tension or compression to force AD. Now it is no more 0, it is 1 unit. Okay, so you can put it as tension, 1 kilonewton, or you can put it as a compression or -1. Are you clear, class?
Yes, Doctor.
Yes, thank you. Yeah, thank you for your feedback. Okay, so now I'm going to show you solving of this N node, okay, or for the exoforce. Okay, but probably I can share you on, a detail for N node. The rest I will just quickly, okay, tell you on what you need to do. Okay, for example, I'm going to solve after I have created the end node N1, N2. I'm going to analyze these three structures. Okay, for truss, you can use method of join, method of section. Okay, that I have shared with you before. And now what I'm showing here is using the method of join, but I'm going to solve it directly on my diagram. Okay, therefore, I'm going to search join by join, okay, to solve for the unknown forces. Okay, I can first, okay, determine the support reaction, because now the support reactions is easily, it can be easily determined. Okay, few have text me and asked and told me that they cannot solve the support reaction for the given truss, what they should do. Okay, so my advice to you is, you now in these methods, uh, concern is actually on the axial force. Okay, if you have given a truss and you cannot solve for the support reaction, you can go for the method of join to solve any axial force in your member first. Okay, then later only, if you are required to solve for support reaction, then you can, you will determine the support reaction later. Okay, so now I'm going to use this considering the whole system. And taking summation MA equal to 0. Okay, so I can, from this system, I can solve EX only. Okay, from this EX, I can use summation Fx equal to 0. I can solve my AX. Okay, my AX should be equal to EX at the opposite direction. Okay, so therefore, here if you can see, my AX is equal to -5. In fact, it should be equal to, in fact, it is actually acting this direction. Okay, so now I'm going to use a method of join, since I already have some of the details. Let's say join A. Okay, so if I can see join A, be careful. If you want to directly solve it here or draw a free body diagram, you need to consider all the forces that are acting at A. For example, any support reactions at A, you need to consider it. And any member force that acting at A, you need to consider it. And also any applied loads on at A. Okay, so you need to consider these three things. Okay, always recheck. Okay, so now I need to use summation Fy equal to 0 and summation Fx equal to 0 to solve my equilibrium at a joint. Okay, so now I found that I have one non-horizontal, which is AB. Okay, and I have AX. Okay, in this system, I have AX and also FAB only. So my FAB must be equal to 5, because this AX is actually acting to my left, and this FAB shall be going to my right to make sure summation Fx equal to 0. So remember, I've told you earlier, okay, you will have one arrowhead for this member AB, means that you already solved for this FAB. Quickly mirror this arrowhead to the other joint, so which means B, okay, here, because you already solved it. Okay, so now your A, you have no more unknowns at A. This AE is not a member. This AE is just a wall. Okay, so it's not a member. Okay, now you can proceed to other join. I will proceed to join C here. Okay, if you want to draw this free body diagram out, there is no problem. Okay, but now if you can see that I will have one unknown horizontally. I do not know the arrow, either it is tension or compression yet. Okay, and then I will have another one horizontal force acting resolved from this member CB, and one vertical force, okay, that resolved from my member CB. Okay, so I directly resolve it in horizontal and vertical only so that I can use this quickly. Okay, so now I have only one vertical unknown at this joint C. Then I solve for the vertical, one unknown first. So I take summation Fy equal to 0. I found there is no other, no exit force, no support reaction, no applied load. So this vertical must be equal to 0. Okay, once this vertical force has been solved, you can find the horizontal components, okay, by using this ratio. Okay, you need to use this value 0. Okay, multiply. Since you are finding the horizontal components, you multiply with the horizontal length divide by vertical length. What is this horizontal and vertical length? This is about the geometry of this slope. Okay, horizontal means the horizontal length, and then verticals mean this length. Okay, so of course 0 multiply h over v, you get 0 here. Therefore, you get this 0. Okay, and you can solve the other unknown as well, this member CD, okay, which is also 0 because summation fx, this is 0, this must be 0. Okay, so you might just no need to write your arrowhead because it is 0. Okay, so you can move to join, let's say join D. Okay, now at join D, class, may I know how many vertical components force, okay, at D?
One,
One. And then how
One,
about horizontal?
two,
Two. Okay, normally we will only solve for one unknown, okay, force. But now this has been solved. Remember, this DC has been solved. We already know. So here at D, we will have one unknown for vertical and one unknown is for horizontal. And let's have a look at summation Fy equal to 0. So there are no other force acting at D. Okay, some might ask, how about 5 kilonewton? Why 5 kilonewton is not being considered? So be careful, 5 kilonewton acts at B, not at D. Okay, so we just concentrate at forces at D only. Okay, so now by using summation Fy, this is also 0. Okay, and this horizontal, of course, this is 0 because there is no other forces, no support reaction, no loads, no other exit force that contains any value. Okay, therefore you have solved for you have left only one member force, okay, in your analysis. You can proceed with E, or you can proceed with B. Okay, so let's try on B. Okay, so now I'm looking at B now. Okay, so I have solved for this BA, which is 5. I've solved for this BC, which is 0. I've solved for BD, which is 0. Now I have left one vertical unknown and one horizontal unknown. Okay, make sure you draw it in the positives. No, what I mean is positive. Yeah, the arrow shall be in positive sign. What is the meaning of positive sign? Means that whenever you get this result later, it shall not have a negative value. It should give you a positive value. Okay, I'm not talking about compression or tension here now. Okay, so let's have a look on the horizontal component. So now horizontal component, I have one unknown here and I have one 5 kilonewton. So definitely this must be kilonewton. Okay, and I can also directly solve for my vertical component, which is I have 5 kilonewton applied load and I have one unknown vertically. Definitely it is 5. So you have already made sure all the forces in equilibrium. You can also check at E later. Okay, once you have mirror this information down. Okay, to make sure all your forces in equilibrium and you have done it correctly. Okay, so once you have solved for N0, you can continue with your N1 using the same method. Okay, into, okay, Then we will go for the compatibility equations. Okay, so I think this compatibility equations is new to you. Okay, and to make sure we get familiarized, okay, with these equations, I will advise you to write few times. Okay, think that yeah, I can write these equations because we are not deriving a new equations here. We are just using the equations that have been derived, and then we just put in the inputs and we solve for the redundant force. Okay, let's try, okay, to write some d equal to 1, d equal to 2, and we write d equal to 3. Okay, so the compatibility equations here deals with displacement. Okay, so we will have delta 1 equal to delta 1 naught, okay, plus delta 1 1 r1. So we want to solve for this r1. Okay, if there is no support displacement, it should have equal to 0 here. Okay, so let's try on d equal to 2. Okay, d equal to 2 will have two equations, which is dealing with delta 1 and delta 2. So delta 1 we will have delta 1 naught plus everything will start with 1. Delta 1 1, okay, r1 plus delta 1 2 r2. Okay, because we have two redundants. Okay, we need to have equations involving r1 and r2. Then we will have delta 2 naught, everything start with 2 now, plus delta 1 2 1 r1 plus delta 2 2 r2, equation number 2. Okay, how about trying together with me? Okay, on this d equal to 3. Now we are going to have d1, d2, and delta 3. Okay, can you help me, class? How to write this delta 1? Start with delta 1 naught. Yes, and then delta
Delta 1
1
1
1 r
R1
r1 plus
plus
delta
delta 1 2
1
R2
2 r2 plus
plus delta 1 3 R3.
ah, that's great. Okay, you can write it. Okay, so then we start with delta 2 naught plus delta
1 R1
1 r1 plus
plus delta 2 R2
2 2 r2 plus
plus delta 2 3
2 3
R
r3. Oops, cannot see. And then delta 3 naught plus
delta 3 1 R
1 r1 plus delta
delta 3 2 R2 plus
plus
delta 2 3 R3.
r3. Okay, so why I want you to get familiar with this is because uh, this naming is also a reference, okay, to get the remaining equations. If you still remember in the virtual work method, when we want to find the displacement, we talk about, for truss, we talk about n L over AE. Okay, now we are going to use this formula as well, okay, to determine all these delta. All these delta are displacement, okay, at a certain location, at your primary structure, at your redundant structures, okay. So now we are going to try one. Okay, how to get this delta 1 naught. Okay, so delta 1 naught, okay, what you need to know is taking the reference from this name, 1 and naught. So meaning that your exoforce should become from 1 and naught. Okay, either you want to put n naught n1, there is no problem. You want to put n1 n naught, there is no problem. Okay, as long as it's come from 1 and naught. Means that n naught is from exoforce from the primary system. And N1 is from your redundant structure number 1 first. Okay, the axial force and then L over AE. Are you okay, class, on this naming? Can we try on delta 2 naught and see whether you can appreciate that? 2 naught, how to write this? Summation?
N2,
N2, N naught, L over
AA.
Thank you. Delta 2 naught, summation?
Summation N3, N naught, L over AA. L over E.
Thank you. How about let's try any of it. Delta 2, 1. Summation. And?
N2, N1.
Right. Okay, so you get the gist on how to write these compatibility equations. Of course, you do not calculate twice. For example, this delta 2 1 and delta 1 2 because they are actually the same. Okay, 1 2 and 2 1 is also N1 N2. And for example, 3 2 and 2 3 also the same. 1 3 and 3 1 is also the same. So when you are dealing with this d equal to 2 and d equal to 3, okay, you need to know about this. You do not need to calculate so many times. Okay. So now, once you have familiar with how to write these compatibility equations, we are going to put these inputs because we already get all these inputs. We already have the N1, N0, N2 from this from your calculation here. Okay, we just need to put these inputs into our equations. Okay, how to do that? It will be more easier for you to put in the table. Okay, just now we said about d equal to 2. We talk about we have delta, wow, I need to rewrite that. Okay, but we have a delta 1 naught, delta 2 naught, delta 1 1, okay, delta 1 1 2 or equal to delta 2 1 and delta 2 2. Okay, to be fine, to be determined. Okay, so this will be delta 1 naught here. Okay, which is a summation n naught n1 L over AE, right? But the L over AE is constant in the problem. So you can put it at the end of your equations later. So for delta 2 naught, you have to calculate n naught n1. For delta 1 1, you calculate n1 n1. Delta 1 2 or 2 1, you calculate n2 squared. And this is 2 2. And delta 1 2, you have, or equal to delta 2 1, you have n1 n2. So now the remaining process is just like a repetitive process. Okay, if you have an Excel file, this will be very fast. Okay, maybe later if you are with the laptop, we can solve one question using Excel file. Okay, but in the test you might not have this equipment, then you might have to use the calculator. So now AB. So we have A, B, B, C, C, D, D, E, A, D, B, E, B, D. All the member, including the one that you are going to remove, AD. This AD, right? In your primary structure, yeah, in this structure you don't have any. So, but you still need to put it in because in the N2 you have this 1 unit force for this FAD. Okay, don't forget about that. Okay, so I'm highlighting this. Okay, FAD, all the members you need to put it in. So you collect all the axial forces from your the solved primary structure, redundant structures. Okay, and put it correctly. And another things to highlight here is the negative. Okay, so whenever got compressive force, okay, you need to put a negative to the value. Okay, so that is why when I advise you in earlier solution, okay, when you get the compression force where the arrow is going into the joint, quickly put a negative here. This negative doesn't mean that your arrow is wrong and you need to change it to the other side. No, this sign is just for the use for this. Just mean this is compression force, and it will be used here, okay, in your calculation later. Okay, so now once you have compute this data, you need to do a summation. Okay, you need to summation of these columns. Okay, then this one you need to put in your compatibility equation. Okay, so I show you part of this the table just now we have obtained because our concern is on this summation. Okay, if you remember the equations that you have derived earlier, okay, you have write earlier. Okay, this is the equation 1, this is the equation 2. Okay, this is the delta 1 naught, delta 1 1, R1, delta 1 2, R2. So delta 1 naught is negative 20. So you just put negative 20 here. Delta 1 1 is negative 10. Oops, 10. Sorry, 10. Delta 1 1. Okay, 10. And delta 1 2 is from here, 2.121. Okay, just put it in this equation. Remember, you have R1 here and R2 and equal to 0. Similarly, you apply the one that from the tables to this equation, delta 2 naught, delta 2 1, R1, and delta 2 2, R2. Okay, so once you have this equation 1 and 2, the unknowns here is R1 and R2. And you can solve your R1 and R2. You can also put it in the matrix form. Sometimes the test will ask you to please put it in a matrix form. Okay, so how to put it in the matrix form? This will be delta 1 naught, delta 2 naught. This will be delta 1 1, delta 1 2, delta 2 1, delta 2 2. So how to name this is actually referring to matrix inputs here. And then you have the vectors of R1 and R2. Okay, then here is my tips for you when you are using a calculator. Okay, uh, you can now try on your calculator's functions on the matrix. Okay, and you can or simultaneous equation in your calculator. You can solve this R1 and R2. By the way, class, what is R1? What is the meaning of R1?
Redundant force.
Thank you very much. So these R1 and R2 are the redundant forces that we have decided and removed earlier. Okay, if you still remember, our R1 is CY. Our R2 is FAD. If not mistaken, let me check that. Yes. Okay, so what this means is you are actually solving the real structure, the CY value and FAD value. And from this, once you have solved for this real structure, you can put it back in the real system and you can solve for all the remaining support reaction and also the axial forces. Of course, here I show you an equations where you can get your axial force directly without using the method of joint. Okay, how you do that? You need the information of the solved R1 and R2, which you obtain from here. Okay, and put it in. Okay, so I go back to the table and now you already solved for R1 and R2. You are going to replace this, substitute R1, the real value of R1 and R2 later. And how to use this equation is you need to get the N naught. Okay, maybe I use here N naught plus N1 multiply with R1 and plus N2 multiply with R2. Okay, so maybe you can get your calculator to try on this, or maybe on this. Okay, I give you 1 minute to do that. Oops, you need the value of R1 and R2. R1 is 1.6. R2 is 2.1. 1.6, 2.1 kilonewton. Can you try on getting this? Okay, maybe I will call a name here. Nurul Aiman.
Yes, okay.
Yeah. So how's your solution? Can you get the value?
I'm still calculating.
Okay. I'll be waiting. 'Done? Anyone?
Doctor, I get 4.
4.04.
Yes.
Wait, is that I copy wrongly? 1.6, 2.1. 1.6, 2.1. How about the rest?
0.32. Member member AB kan, Doctor?
Member A, member AB. I'm talking about member BE right now.
Oh, right.
Doctor, I get 3.65.
This is scary. This scared me. Let
I
me
also
check.
get 3.6.
Okay. Three point six five five, is it?
Yes, yes,
Yes.
doctor.
Yes.
Doctor.
Yes.
3.655. All right, then you might have something extra to do today to check all these forces whether it is correct or not. Okay, same with me. So, but how we get is from these equations. Okay, so I might want to check back this n0, n1, n2 whether it is input it correctly. Okay, so this is how we do it. Do you want to try on using your calculator to solve this R1 and R2? I will give you maybe a minute or two to put in your calculator and see whether you can get this value. Can I switch a bit? It's getting more different. Do you get this? But I get 0.48 and 0.75. How about you?
Yes, but negative.
You get negative 0.45. Are you using the equations in your calculator? Because this calculation, you need to look at this, the form. The form is ax plus by equal to cn. So this c is you need to put it there.
Doctor.
Do you do that?
Not.
Doctor, I got the same.
Yeah, you get same, right? This one?
No, I got the same as the slide 1.6 and 2.1.
Really? So
the one that should be equal is negative 20 and negative 10. Sebab R1 dengan R2 ni patutnya duduk dekat depan. Ini yang kena bawa ke belakang.
yeah, correct. This is the one that need to go at the back. Thank you. Sila. This is C. So you get this, right? Okay, luckily satu pun betul. I thought that I need to relook all the things. Okay, be careful on your equations. Okay, the other ax plus by equal to cn. This is what being written in my calculator. So this c will be referring to this. This is c. Okay, betul lah, ha? Betul kan? Okay. So, wow, it's a good exercise this morning. Okay, how about taking a 5-minute break? Okay, let me check the attendance. And then we are going for a 1 tutorial question. Okay? So,
Okay, Doctor.
yeah, you can have a break for a while. Let me check the attendance. Okay, we have Nurul Aini Nadira. Are you here with us? Cannot find. Why? Nurul Aini Nadira. All start with N. Can you see? Or maybe your friends who are very close to Nurul Aini Nadira. Can you help? Okay. To notify her. Okay. One more. Truss. Okay, then. Hmm? Okay, class. Shall we start? Are you all here with me right now? Okay.
Yes.
So if you notice that I have give you a I discuss tutorial question, A shall be tried in my first class, and the second question will be on this one. Okay, if you can you see my screen right now?
Yeah.
Yes.
Okay, so there are two questions. Okay, yesterday class I have tried on this question A. Okay, today class we are going to try on this question B. Okay, so let's try. Okay, and if you notice that this question B, we have a different area. Area is not constant, and we are going to put it in the table right now, the table later. And we need to determine the support reactions and all the internal forces. Okay, using this force method is flexibility method, and use the specified redundant force. Okay, redundant force has been given to you, FAD in this case. Okay, so now can you try to draw your this problem quickly, and then draw the primary structure and the redundant structure. Okay, I give you 3 minutes only. Okay, then we will start on analyze this structure. So it might not be a very beautiful one, just a sketch, but make sure it is big, okay, for your primary and the redundant structure, N0 and N1. Yeah. Okay. So, have you done?
Yes, doctor.
Okay, so now let us have a look on the primary structure. Is that oh my this structure is not right. Okay, so this is a primary structure. Have you got this?
Yes, doctor.
Okay, but the N1 I have something wrong with my N1. I need to fix it. My N1. I should delete this. Okay, this is my N1. Okay, then let's try on solving the N0 first. Okay, so we have EX. I don't have any answer with me, so please check my calculation. So I will have EX. I have EY. I have BX. Okay, I would like to take I can actually solve the member force CD right now, okay, which is supposed to be 0. I can just solve it, okay, because at D there is no other horizontal force, okay, so this is 0. I can also solve for member AB actually. Okay, why? Because I'm if I look, are you following me right now?
Yes.
Yes.
I worry that I would just too fast. Now I'm looking at joint A. Okay, I have found that I have one horizontal unknown and one vertical unknown. So I can solve for these unknowns. Okay, for this member AB, there are no other horizontal force. Therefore, this is 0. Okay, but this unknown vertical AC, the vertical unknown at A, I have another load, 75 kilonewton, which is acting down. Therefore, I will have another one acting up. At A, I'm looking at A now. Maybe I will just skirt so that you know where am I. So now this is 75. I quickly mirror my arrow. Okay, so now if I go to B, go to join B, I cannot solve it because I have two horizontal unknowns, which is BX and one is in BC. And I also have two vertical unknowns, which is in BC and BD, cannot solve. So I go to D, I have two vertical unknowns, cannot solve. I go to E, I go to C. Yeah, there are just too many unknowns I cannot solve. So I have to solve my support reaction first. Okay, here I solve for my support reaction. Or you can use the method of join, okay, to solve at C. You can solve it by using a simultaneous equation. Okay, but now I just want to find my support reaction. I take a summation. Let's say summation moment at E equal to 0. So I have Bx, 9 Bx. I have 75 with the distance at. I have 60 with the distance 3 equal to 0. I recheck back. I have 9 Bx. I have 75 with at. I have 60 with 3. Okay, 75 and 60 is negative, and then this is positive. So what is my Bx? Okay, can you help me? What is my Bx?
Negative 86.67.
Oh, very long. 8.6.
86.67.
Okay, 86.67. Negative 86.67. But I don't like actually negative. So I would like to change my Bx.
Wait. Positive.
Dapat
I
positif,
forgot
doktor.
to.
Dapat
I
positive.
forgot to change the.
Okay. So this direction is correct, right? This direction is okay, thank you. So now I've solved my Bx. I actually can continue with all this, okay, without solving my Ex and Ey. Let's try. I'm at B. I know my Bx is 86.67. So I have only one horizontal unknown now left, which should be 86.67. Okay, balancing this Bx. At B, yeah, I don't see at other joint, I see at B now. Okay, so I can get my vertical components. How? 86.67 multiply vertical heights. Oops, no, wait. I go further. 86.67 multiply vertical height divided by horizontal height. Okay, which is vertical height is 6 and horizontal height, horizontal length is 8. Okay, so I get, it's difficult for me to write. Wait. So, or equal to 86.667 6 divided by 8. Okay, what is that value?
65.
65. Oh, sharp, huh? So now can I get this exoforce for member BC? This is 65. This is 86.67. How much? It will be negative force. 108.
Yes.
3, 4. Okay, so now I can solve for joint C. Okay, or joint B, there is one more left, vertical. Okay, vertical, which is 65. Now, I think if you can see that we have one to non 465, and oops, this I shall go back. Okay, maybe a bit bigger. So I will have 65 going up. So this is tension, and I can solve also DE right now. Okay, because I have one dB is 65 going down, so I must be having another one going up. So still tension 65. Okay, so if you can see that, you cannot solve at E, because at E you still have two horizontal unknown and two vertical unknown. So I move to C now, because I'm lazy to find what is in EX and EY. So now I have 75 vertical unknown going down, and I have 65 going up. So how about my unknowns, vertical unknowns in CE? Do you think it's going down or going up?
Going up.
Going up, yeah. How much?
10.
10, thank you, because 10 plus 65 minus 75 equal to 0. So I can't use my these ratio methods to get my horizontal components from here. So it will be 10 multiplied with horizontal distance is berapa? 8. Yeah, 8. Okay, 8 divided by the height is 3. So I get 80 divided by 3. How much?
26.67.
Yeah, 26.67. Can you get the, what is the exoforce for member AE?
28.48.
48, is it?
Yes.
Okay, so this is tension. So now you have complete all your exoforce. You can move to N1. But I want to check back my C, whether it's in equilibrium in horizontal. Okay, I check first. So 86 minus 26.67. Oh yes, yeah, I've achieved all this equilibrium except E. I do not check. I do not determine the EX and EY, but I have satisfied with this. So now I will move to N1. Okay. So for those who are fast, you can yeah, continue with without waiting me. So now this is N1, where I apply back this 1 kilonewton, but now I already have my arrow in compressions. Okay, so I will just continue with this. Okay, compression. You can put it in tension, no problem. Okay, so now I can resolve this 1 kilonewton also, okay, in the horizontal and vertical components. How to do that? Okay, you just need to get some of the angles, maybe this angle. Okay, so how much is that angle? Can anyone help? 36.9, about, right? 36.87, something like that, but I just put 36.9. So now you can resolve this into horizontal by multiplying with cos theta and vertical with sine theta. Okay, so this one you can get it in such a way. Don't use -1, just 1, because your arrow already means minus here. Okay, 1 times cos 36.9, you will get 0.8 here. And oops, I don't have much space here. 1 sine 36.9, you get 0.6. I hope you can see this clearly. Oops. So you can refer here 0.6 and horizontal is 0.8. Okay. So now I can start with maybe my joint A.
Doctor,
Yes.
the 75, should we remove it?
Yeah, thank you very much. Yeah, I have removed the 60, but not yet with this. But how shall I do that? Thank you for reminding. I have to again press here. Okay, so now we are go back to this joint A. Okay, my joint A, I will have one vertical unknown and one horizontal unknown. Okay, I can immediately solve my, this will be 0.8. Okay, and this will be my 0.6. Okay, so I will move to join D. Okay, join D, I can solve for the horizontal unknown. Okay, which is this one. So I will have 0.8 here. Okay, but the vertical unknown I cannot solve because I have two vertical unknown at D, so I cannot solve for that. I will need to move to other join, okay, to seek for only one unknown. But I cannot continue anymore, right? Can I? See, there are two. Okay, you can use the method of join, okay, for this case, for C, okay, that I mean, solving the two simultaneous equation. Or at, oh, at B. Okay, probably we can choose to solve at C. Okay, with this, let's see, join. Okay, I have this CE. Okay, and then I have another one is F, CB, and I have 0.8, and I have 0.6. Okay, I have this angle and I have this angle. Okay, let's say I cannot write it here. Let's say this is theta, this is alpha. Okay, so my theta is, I will get my theta 3 divided by 8. 3 divided by 8 is 20.56, and my alpha is 6 divided by 8. Should be same with it. 36.9. Okay, now I have this FCE summation F x equal to 0. FCE cos 20.56 plus 0.8 plus FCB sine 36.9 equal to 0, and summation Fy equal to 0. I have FCE sine 20.56 plus minus FCB, oops, wait, this is cos. Okay, FCB sine 36.9, okay, minus 0 equal to 0. So I solve for this number 1 and number 2. Okay, I check back FCE cos 20 plus 0.8 plus FCB cos 36.9. Okay, my FCE sine 20.56, okay, minus FCB sine 36, okay, 0.9 minus 0.6. Okay, so can you solve for me that what is FCE and what is FCB? Get this? Do you get this?
Yes.
Yes,
FCE
Doctor.
is 0. So I just put it 0. This one is 1. Okay. Say -1. Okay. So I believe that this is also the same as 0. This should be 0.8. This is 0.6. Can you check back? Okay, this is 0.6 and this is 0.8. Okay, so now we can solve for vertical. We can solve for B now. Okay, so the vertical component is left 1, which should be 0.6 here. Okay, tension. Am I right? Okay. Yes. So now you have solved for member A, B, D, and we can go back to D to solve for member DE. Okay. So this is 0.6, 0.6 going up. So how much? DE, can you solve for me?
0.
0, yes, it is 0. Then you can't prove that in these systems, okay, this is all 0. Okay, so if you already know that this is all 0 because there is no applied load, okay, for your BX, EX, and EY, actually you can skip this step. Okay, just directly solve for the member EC, ED, and so on. Okay, so now you already solved for N node and N1. Okay, I want you to gather all the information in your table. If you have an Excel file with you right now, please do it in Excel file. Okay, because I'm going to create mine. Have you done with this step? Have you done with this slides, class? Can I move to my new
Yes.
slide? Okay, okay.
Yes.
Okay, so please create your own table in Excel if you have. If not, then you need to put in, draw the table in your exercise book. Okay, because I'm going to create mine here. Okay, do yourself. If not, you will be confused looking at me changing all these things. Because I do not have a printout version, I need this to guide me. Okay, I have AB. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, then this length AB is 8, AC is 6, B is 6. AD is 8, BC CE 73, 8.544, CE 5, DE is 3. We have the area not constant in this. Okay, how to insert column? Right or left? Right. Oops. AB. Now put CD, BD1, CD2, CA1, BC2, AD2, CE2, DE1. Okay. How about you? Are you filling the table?
Yes, doctor.
Okay. So I'm going to this indicator. This is 0, 5, 80. CD is 0. And then the AC is 75. BC is and E is 0. CE is 28. And DE is 65. AB, BD, BD 65, 0, 75, negative 0, and then 28, CE, and then DE 65. Okay, then I go to int 1. Oops. Oops. Let's come back to here. For those who have done, wait me for a while. Okay, so AB is 0.8, D is 0.6, CD is 0.8, AC is 0.6, BC is -1, AD -1, CE 0, and DE 0. Done. Check AB, AC, CD. Okay, so AC. Okay, done. Okay, in my Excel file. Here I shall have L over A. Okay, L over A. Okay, so copy this, maybe like this. Here. Okay, so okay, plus this multiply this multiply divide by my area. Okay, so then this multiply length divide by the area. Yes. Then I have my summation. Just copy to this. So I have to copy both things here and then back to my oops. Okay, class, where are you right now? Are you completing your table? I want to check my answer with you.
Not yet.
Not yet.
Doctor,
Yes.
AD
AD.
untuk area dia
Area.
1.
1. Wait, let me check. Apa saya salah letak? AD.
Oh, okey, saya yang salah.
Okey ya, 2 betul
Okay, okay. Yeah.
Okey
Yes, betul.
Okay. So now I can write my compatibility equations. Okay. Okay, let me know if I'm doing some mistakes. Okay, delta 1 equal to delta 1 naught plus delta 1 R1, which is also equal to 0. Summation N1 N naught L over B plus the summation N1 square L over A. Okay, equal to 0. This will be
Pas pulang kah balik?
7. Okay. This should be in terms of A because A is not to you. Okay. So you will have over AE plus 22 over AE R1 equal to 0. So R1 is equal to negative 47.5 kilonewton, which means that it should be in tension. Because my earlier assumption is it is in compression. So if I get a negative, meaning that it should act a different direction. Okay, but I hope what I have done just now without mistake. So my R now is 47.5. So I can put it R1 is 47.5. My R1 is actually my F apa lupa. My
FAD.
AD. Thank you. Okay, so now I would like to put back this in my Excel file. Okay, those who don't have Excel file, you can use a calculator to compute this. 47.5. So my R is 47.5. So all R is the same. So now I need to get in just to show you this. Okay, Excel file. Okay. So I will have plus N naught plus N1 multiply with my R1, and then it is very small. I will put it down, and I shall have ED. Sorry, the R is in negative. Okay, then this is correct. So now I go back and paste it in. Okay. So I can also find my support reactions later, but I want to see my files. Here's my file. Oops, this. Source key. Fine. Okay, answer is given here. Let's check our answer. So FAD is 75 tension. FDE is 65 tension. Okay, supposedly, but it only give FAD and FDE for us. All right. So enjoy trying. So I will stop recording now because I think this lesson is just lengthy. Okay. So how about you? Any questions before we end the class? Okay. Maybe I will ask a few of you. Damia, are you okay, Damia?
Yes, okay, Doktor.
Okay, where are you right now?
Calculating the end value.
You have Excel file with you or not?
Saya tak buka.
Oh, like that. So you need to use calculator, right?
Yes.
I think it's still fine. Tak ada banyak sangat. Okay, I check. Let's try Azira. Azira Raniza. How about you? Are you okay?
Tengah kira.
Masih tengah kira, macam robot, So let's see. How about Maliana?
Dan, Doktor.
Done. Okay. So I believe you are using Excel file.
Yes, Doktor.
Macam tu, So how about Rabiatu?
Tengah kira, Doktor.
Pakai calculator
Yes.
Okay. So kita tunggu sekejap lagi, then we will close the session. Tapi ada apa-apa yang nak tanya tak? Yang tak faham ke proses dia?
Doktor,
Ya.
kan Arwan tu dapat negatif kan? Kenapa jadi tension?
Sebab pada awalnya, asalnya kita assume dia, saya patah balik, kita assume-nya negatif 1, nampak tak? Kita assume dia compression. That is why sekiranya kita dapat result kita negatif, kita sepatutnya, maksudnya apa yang kita assume ini terbalik. It should not be in compression, it should be in tension. Siapa yang bertanya? Sekejap. Siapa yang bertanya?
Ulang balik, Doktor.
Kita dapat R1, sekiranya kita dapat negatif, maksudnya kita punya assumption pada awalnya, kita punya R1 silap. Sebab sebelumnya kita assume dia compression. Nampak tak? Yang ni 1 kilonewton FAD. Dekat itu N1. Negatif 1 kan? Kita assume dia compression. Kita assume dia arrow-nya pergi ke towards the joint. Tapi kita dapat negative value. Maksudnya apa yang kita assume itu salah lah. Kita sepatutnya terbalik. Yang betulnya actual real punya force adalah terbalik. Okay, so sekiranya siapa saya nak panggil nama, saya tak tahu nama siapa. Siapa?
Fahana.
Fahana. Fahana, sekiranya sepatutnya tadi saya pada awalnya saya patutnya assume dia tension supaya you tak confused. Maksudnya jika tension you dapat positive value, tension lah dia. Tapi jika you dapat R1 tu negative value, compression lah dia macam tu. Tapi saya telah buat saya punya arrow tadi masuk ke, saya malas nak tukar. Jadi lain kali untuk Farhana, jika you rasa confused sangat, semua yang redundant force ini you assume the tension.
Faham.
Nanti you senang sikit. Okay?
Okay.
Apa lagi?
Okay, thank you.
Okay, jika tak ada soalan, saya rasa saya akan I have to close the session. Yang tak siap itu kena siapkanlah. Saya akan snap screenshot yang ni untuk you dulu dalam WhatsApp group. Tapi nanti at the end of today ataupun tomorrow, I will send you the whole PDF file. Okay, including yang tutorial yang saya buat dengan kelas lain. Tapi tak ada dalam record video. Okay, which is this one. Which is this A punya problem. Nanti saya akan sharekan. Okay, you can check lah. Okay, class. I see you next class. I mean, we cannot be forever at Truss. So next week we are going to apply this flexibility to beam pula. Okay, so I hope you can make
Okay,
sure you
doktor.
practice tengok balik kita punya note supaya you faham macam mana nak buat itu flexibility. Okay, I see you next week ya. Bye bye.
Okay, doktor.
Thank you,
Doktor.
doktor.
Thank you,
Okay,
Doctor.
doktor. Thank you, doktor.
Thank you, doktor.
Bye.
Doktor,
Yes, I still here.
saya nak tanya yang
Yeah.
if let's say macam yang kita punya virtual punya structure tu,
Yeah.
and then kita yang first assumption tu kiranya tak kisahlah sama ada kita nak assume dia tension ataupun in compression.
Tak kisah. Nanti itu jawapan akan beritahu you punya assumption betul ke salah.
Lepas tu madam yang pasal yang arrow tu kan yang macam kita dah dapatkan force dia,
Yeah.
saya a bit confused macam ni kita nak tahu dia punya apa dia punya macam yang tadi tu dia punya force from yang untuk length tu kan negative 108.35 kan madam kan.
Yeah.
Kita kan dapat arrow macam kiranya macam ni nak tahu dia punya tu compression negatif ataupun dia tension.
Sekiranya daripada yang apa yang kita buat tadi, kita if not mistaken kita mula dengan B
Kita B.
kita analyze B, kita dapat ini sebab kita sudah tahu ini BX 86.67. That is why kita pun telah tahu AB itu kosong. That is why yang the only left unknown itu dia pergi ke arah sini 86.67 kan.
Yang mana kosong madam?
Yang ini kita sudah awal beritahu AB adalah kosong. Kita solve at A pada awal-awal mulanya.
Okay.
Jadi the left unknown adalah yang ni saja. Therefore kita boleh tahu dia 86.67 untuk balance up with this BX. Okay. Jadi once you already know that the arrow is going here, so you kena tahu yang resultant force mesti di tengah-tengah yang vertical and horizontal component. Jadi arrow akan lukisnya sebegini. Jangan lukisnya di terbalik pula. Macam ni. Boleh faham?
Macam mana madam? Boleh.
So what means that we already know this. The next punya you mesti draw supaya ini resultant ini di tengah-tengah both forces ini. Okay?
Okay.
Baru you boleh tahu ini resultant force adalah ke arah ini.
Okay madam.
Ini kan dia menuju ke B.
Menuju ke B.
Arrow jika dia masuk ke joint tu kita kata dia compression.
Okay.
Arrow yang keluar daripada joint itu tension. Okay?
Okay madam, thank you.
Lukis lagi. Jangan lukis macam ni. Jangan.
Jangan apa?
Jangan lukis sebegini. Jangan lukis macam ni. Yang
Macam
saya
mana?
macam ni. Nampak tu? Oh, you
Tak
you
nampak.
Aduh, saya ni conteng banyak benda tapi you tak nampak. Okay, saya kena tunjuk. You kena beritahu saya you tak nampak saya punya screen. Alright, jadi yang ni kan you punya force tadi you dapat
86.87.
Ya, you nampak saya punya screen sekarang?
Nampak.
Jadi untuk vertical component itu pastikan ini result ini dilukis di tengah-tengahnya. Macam ni. Jangan you lukis macam ni pula.
Okay.
Jadi once you boleh lukis macam ni, you akan tahu dia punya itu arrow-nya untuk resultant adalah ke arah ini.
Okay.
Then you boleh tahu dia arrow ini adalah ke arah joint ataupun keluar daripada joint. Untuk yang ni ke arah B. Jadi dia forces ini resultant ni adalah compression. Boleh faham?
Boleh.
Ini yang saya cakap, jangan lukis macam ni, jangan.
Okay.
Okay.
Saya tengok tengah-tengah. Okay, thank you madam.
Okay.